So I'll talk briefly about approaches to date. The oldest and best researched solution to reflected signals depends on GNSS-INS integration. And this is found in cars, and automatically your smartphone will engage INS-GNSS integration if it senses that it is mounted in an inertially stable way in your car, i.e. Mounted on the dashboard, for example. This is a good reason, by the way, to mount your phone on the dashboard if you're navigating with GNSS in your car. So if you do that and you drive from outside a city to inside a city, it essentially solves the problem for several minutes. You may have experienced this, that GNSS from a smartphone on a dashboard does work pretty well when you drive into a city. But the INS does not help you if you start up within the city, or you do a lot of stop-start driving, such as if you're a professional, like an Uber or a Lyft or other kind of taxi driver, or you're a regular driver in dense city traffic, or you spend too long in a dense urban environment. So this alone is not the solution. The next most researched solution is something known as shadow matching, you've no doubt heard of. I'll briefly use this picture to explain it. So what I'm doing here is making an analogy with the sun. It's just an analogy, but if you imagine that the sun is up here behind the satellite, which it is in this photograph, you can see the shadows from the sun, and someone told you, oh, I'm standing in the shadow of this building, well, you'd have an idea where they are. Conversely, if they were in the sunlight, well, you've got an idea as well. Well, shadow matching is doing the same thing with satellite signal strength, typically measured by carrier to noise density ratio, CN0, in the phone. And so with this particular satellite, there is a satellite in this location, in this example, and this is the heat map generated from the CN0. If the CN0 is weak, you'd expect to be in the blue, because that's the shadow of the buildings from the satellite's point of view. And if the CN0 is strong, you expect to be in this brownish red area. You do this for all the satellites, you can do a good job of figuring out where you are just from these shadows. So all you have to know is the difference between a strong signal and a weak signal, and there's the problem. In that location that I just showed you, here are the GNSS signals, the CN0 of the signals over a few minutes. And as you can see, there's just no obvious way to draw a line and say, well, these are the strong ones and these are the weak ones. Well, we can bring some order to this, and we've done that by using ground truth. So the blue here shows the known ground truth as we walk around this building. And then at each point, we work out using building models whether a satellite really was a line of sight in blue, i.e. it came straight from the sky, or non-line of sight, meaning it bounced off those bricks or the concrete or something, so we make it brown. And then that very same picture I just showed you, we color in the satellites blue for the line of sight ones and brown for the non-line of sight, and it looks a bit more ordered. You see blue generally on top, brown generally on the bottom. However, at any moment, you'll notice there's some blue ones here that are weaker than all the browns, and there's some brown ones that are stronger than most of the blues. And if we do a histogram of the signal, you'll see the same thing. And so what you're seeing here is that in a smartphone, there is a large variability in the measured CN0, and simply looking at strong and weak satellites is not enough. Furthermore, trees create a problem. You might have line of sight with respect to a building, but be under a tree, and that'll give you weak signals. And you see this in these histograms. And so what this shows you is that shadow matching provides useful probabilistic information, but not the whole answer to the problem. There's another technique known as 3D model-assisted pseudorange matching, and this goes as follows. You create a grid around where you think you are, and at each point in the grid, compare the measured pseudorange to the predicted pseudorange, including the non-line of sight paths. So as shown here in this paper or this lecture by Paul Groves at University College London, and you find the grid point with the best fit. This technique has also shown some promise. The challenge here is computing the rays, because you have to do ray tracing, which I'll talk about more later. But in a lot of papers that analyze this, they've concluded that the ray tracing computation eats up like 1 second of ray tracing on a PC uses 1 second's worth or more of PC CPU, and it's just very computationally intensive and a problem. Also, of course, you need 3D building models with good accuracy. So in summary, the approaches to date, INS integration works great if you drove into a city, but not great if you've been in the city a while or you started up in there. And then i.e. pedestrians or cars starting up in the city, promising ideas are shadow matching, pseudorange matching. Pretty much all the research that I've seen on this, and there's a lot of it, but all shows small trials, meaning 1 to 10 data traces in the paper, and usually in a single city. And there are many unsolved problems, some of which I've just mentioned. And bottom line, nothing deployed at scale, meaning something you could go out and find in your typical smartphone before 2020. I wanted to put up some notable research that's I'm very familiar with that I wanted to share with you. In terms of shadow matching, Paul Groves of UCL essentially started that about 10 years ago, has written about 70 papers, so by far the best published in that area. UC Santa Barbara, a group led by Andrew Irish, subsequently moved into Uber, did something called shadow mapping, which is shadow matching plus SLAM. And then there's other references there which might be useful to you. This is by no means comprehensive, but if you start with these authors and then follow from their references, I think you'll find everything that's out there.